All right. So my name is Jorge Meneses, and I am a member of the board of directors of EERI, and also the current president of the EERI San Diego chapter. So on behalf of the EERI, I welcome all of you participants to this, the fourth Kenji Ishihara Colloquium series on earthquake engineering. So this year, we have two topics. So the first day today, the artificial intelligence applications in earthquake engineering. And the second day, impact of climate change on community earthquake resilience. I've been in touch with Professor Kenji Ishihara. He's apologizing because he cannot make it this time. But I'm conveying his best regards and greetings and wishes for a successful event today and tomorrow. So thank you very much to all the speakers for participating in this event. Thank you very much for all the attendees who are participating in these events from all over the country and from all over the world, different time zones. So good morning, good afternoon, good evening. And for those who are in different time zones and cannot make it to the end, these events today and tomorrow will be recorded. We want to thank our sponsors for this colloquium, FEMA, the California Geological Survey, the Natural Hazards, Risks, and Resilience Research Center at UCLA, Degenkolb, RMA Companies, Tensar, Kleinfelder, Keller. So thank you very much to all these sponsors for their support to these events. For those who are interested in PDH certificates, they will be available next week upon request. And also the entire colloquium will be recorded and will be available. Stay tuned for further instructions because it will take time. We are recording the entire session, so then we have to go through a process of editing, etc., etc. So this may take some time, but we are going to let you know when this is available and how to access to the records. So to have an official opening of this event, we have here the chair of the Department of Structural Engineering here at the University of California, San Diego, Professor John McCartney.
Thank you, Jorge. So I'd like to welcome everybody here to this colloquium for the fourth Kenji Ishihara seminar. We're very happy to host this event this year at UCSD. In the past, it's been at San Diego State. I participated in a couple of the previous events, and they've always been very successful. So happy to have it here at UCSD and also virtually this year. Earthquake engineering is definitely very important to our department. We're very excited that our EERI student chapter is going to be helping out. Looks like some of the students haven't arrived yet in the morning, but hopefully we should have more participation later in the day. I'd like to thank Jorge and our faculty member, Gilberto Mosqueda, who is part of the organizing group for this colloquium. And I apologize for some of the construction noise that is probably going on in the background. The university seems to keep building and building and building and breaking things down, building new things. In the background here, we have a new amphitheater that's going to be, I suppose we'll have fun back row seats to some of the concerts going on. It's going to be the main place for major concerts and stuff like that on campus. And then they're also building in the background a new student housing area. But with that, I'd like to welcome you if you have time during the day to walk around and see some of the different earthquake engineering research that's going on campus. We have the SRMD building, which is right next door. They're testing some seismic dampers right now. Over in the Powell lab, we're getting ready to do a shake table test on seismic isolation using tire-derived aggregates. And if you have time to go to the large high-performance outdoor shaking table at the Engelgroup Center, it's 20 minutes away from here. They're halfway finished constructing the 10-story tall wood building. So it's going to be a pretty cool structure once they're finished. But with that, I'd just like to have a brief welcome and thank you all for coming today. And thank you, everyone who's attending online.
Thank you, Professor McCartney, for the opening remarks. Okay, so next in the program, I'm going to make some, again, this doesn't want to work. It was working. We have our speaker for session number 1 ready. Okay. Oh, yeah, stop share maybe. All right, so let me see something here first. So, yeah, some instructions about how to participate. Some suggestions here: mute your mic to participants. I'm not sharing the screen, you mean?
Yeah, right.
Okay. All right. So please mute your mic for those who are remotely, of course. Rename yourself just in case there are some conflict with your name appearing on your screen. Set the gallery view in this way, gallery. And then the view presentations, use the side-by-side mode. And then you can use here this, with your mouse, you can control the size, of each side. And then for asking questions, you can use the chat options. This is what is suggested here, okay? So use the chat options for questions. So then the speakers, we will respond the questions. So, okay, so maybe we can, I think all the speakers are ready. So probably we can start with session number 1. So the session number 1, we are going to have 3 speakers. Professor Krishna Kumar from the University of Texas at Austin, Professor Adrian Rodriguez, Virginia Tech, and Professor Mohsen Zucker, Utah State University, and then Professor Scott Brandenberg from UCLA. So what we are going to do is that we are going to have these 3 presentations back to back, okay? 30 minutes each. So Scott said that he will do his best effort to fit 150 slides in 30 minutes. And then we are going to have a 30-minute session for questions and answers. And at that moment, please, you can ask questions to the speakers, okay? And during the presentation also, of course, you can send via chat your questions. So when the time comes, the speakers, are going to address questions and comments, etc., okay? And then after the discussion panel, we are going to have a 15-minute break. So this is the plan for session number 1 this morning. So we have 2 presentations here in person and 1 presentation remote. So the first speaker is going to be Professor Krishna Kumar from the University of Texas at Austin. And the title of his presentation is, Can We Trust Artificial Intelligence Models in Earthquake Engineering? So, Professor Kumar.
Thank you so much for the invite. I'm really happy to be back in San Diego. I'm Krishna Kumar. I'm an assistant professor at UT Austin. I mainly work on numerical modeling, and my work in machine learning is developing algorithms to derive physics equations out of machine learning. I work a lot with Professor Alan Ratchey at UT Austin, who's the director of Design Safe, and that's where all my earthquake engineering comes from. So if you have earthquake questions, ask her. But I'll be happy to answer machine learning questions. So because I'm the first speaker, I'll make sure we all start with the good terminology of what we mean by AI, machine learning, and deep learning. Whenever we say artificial intelligence, the first thing that comes to our mind is Skynet from the movie Terminator. We don't have that. That's the general artificial intelligence. We're trying to have computers behave like humans, and that's probably not going to happen, hopefully, in our lifetime. I'm not sure whether that's good or a bad thing. But most of the talk today is going to be mainly focused on machine learning and deep learning. Machine learning and deep learning are a subset of AI. There are quite a lot of specific tasks done by AI, but machine learning is a tool or a set of algorithms. It can be as simple as a decision tree or a simple linear regression. Those are machine learning algorithms, but the machine learning algorithms can also become more complex by using neural networks. Neural networks are trying to mimic neurons in human brains. Each individual neuron in a human brain is much more complex, whereas a perceptron in a machine learning model is a very simple function. The way machine learning models are much better is they do a lot of these simple operations together, leading to much more complex nonlinear functions. And a subset of this machine learning algorithm is deep learning. And deep learning is using a lot of these neural networks. And previously we may have 2 or 3, now we can go 50 or 100 layers of neural networks. That means we can model much more complex systems. So deep learning kind of took off about a decade or slightly over a decade ago and has been the most popular driving tool in AI and machine learning. So whenever we say AI, we're probably talking about machine learning or deep learning in particular. So AI is good, and we don't want to use it as a hammer and everything we see is a nail kind of problem, but we want to use it wisely. We have a lot of science which we've developed over several hundreds of years, and we want to use AI to discover new science and help us solve much more complex problems. Like I said, the machine learning covers a wide range of fields. So from simple classification rules, which are highly interpretable, you can see why we made a certain classification, or linear regression. You know what the exact equation is, what is the error from that equation. And as we go up more and more in terms of complexity, the models become much more accurate. So the neural networks are probably the most accurate models, but along the horizontal axis in terms of interpretability, I won't be able to explain why a neural network made a particular decision. And there's always a trade-off between, is it more accurate or can I explain it? And we are all engineers. We don't like something which we can't explain, and we don't like to use things which are harder to convince people. But we want to be somewhere on the top right, where we have accuracy, but we also have interpretability. That's the direction we want to be going. We often tend to go more towards accuracy and forget about the interpretability part. There are models, I'll show a smaller one today, where we will talk more about interpretability and accuracy and balancing that act. So I'm going to talk about 3 different applications today. One, we'll start from the bottom right, which is highly interpretable, and keep going up the axis. Going to talk about lateral spreading as one application. The other is doing subsurface imaging, and the third is more a peek into the future, because I only have 30 minutes. So where we're going to talk about how can we use AI to make it a PhD student deriving equations. You can let your AI derive equations and write papers for you. So there is a big promise at the end. So this is the work done by Professor Ratchey and Durante on predicting the lateral spreading in New Zealand after the 2011 Christchurch earthquake. So here you see observations of which regions and in the Christchurch area kind of experienced lateral spreading. So they said anything about 0.3 meters to have experienced lateral spreading, and anything below is no lateral spreading. So we want to develop a machine learning model, but instead of looking at soil parameters, they wanted to use proxy parameters. So how far away is a particular site from the river, how tall that particular site was located, that is its elevation, how steep the slope was, and what is the groundwater depth. If the groundwater depth is closer to the surface, you experience more likelihood of liquefaction and peak ground acceleration. So they wanted to use these 4 parameters, elevation, slope, groundwater table, and PGA, and see if we can predict lateral spreading or not. So this is a good problem to do in machine learning because we don't have an exact science for this. So what we do is start off much more simple. The simplest one, a very fully interpretable one, is called the decision tree, where you can start off with any criteria. So they started off with slope and say if the slope is greater than 2 degrees, maybe it's likely to fail. And then L is basically how far the site is located to distance from the river. So if it's closer to the river, it's more likely to experience liquefaction or lateral spreading. If it is further away, then it's less likely. Same for groundwater table or groundwater depth. So how deep the water table is from the ground surface. So you can look at it and just go through the chart, or it's more like a flow chart, and figure out what the condition is. So given a site with a slope angle of 5 degrees, closer to the river, groundwater table is below 1 meter, it's going to lateral spread. Everything is explainable, but if you use this model, you only do about 60% prediction accuracy, meaning it's slightly better than flipping a coin and saying whether it's going to lateral spread or not. Just better, but not the best way to do it. So, which is why we want to bring in more complex algorithms, which are useful to improving accuracy. So one of the slightly advanced decision tree model is called random forest. Have you ever done this guessing game of guess how many jelly beans are there in a jar? And the usual strategy is ask everyone in the room and take an average, and you will always achieve the correct answer. So random forest is something similar. Instead of taking one decision tree and figuring out the answer, the laws of large number works this way, where you create multiple classifying decision trees. So instead of having one decision tree, which you see in the left, you end up having hundreds of these decision trees. Each tree will have its own classification node. Maybe one will classify the slope at 2 degrees, other might do at 2.5 or 3. So same thing with PGA, elevation, slope angle, but you now aggregate all that answers together to figure out whether a particular site liquefied or not. So if you ask someone who guessed the jelly bean, they might be able to tell you why they made that decision of 50 jelly beans in the jar. But if you asked everyone and took an average, there's no way you could explain why everyone made that decision. But you will still be able to look at individual decision trees in the random forest and see why it made that decision. But collectively, you will never be able to explain why random forest algorithm made a decision towards lateral spreading or no lateral spreading. And this is the problem we have. We have a model that is now 80% accurate in predicting lateral spreading. So the random forest algorithm for lateral spreading, you can see the greens are correct prediction. That is, it was able to predict correctly that a site liquefied or not liquefied. It still fails, but the failure rate is much lower at about 20%. But now we have a problem because we don't know why it is predicting at 80%. And because we don't know, can I go outside of New Zealand and use the same model, or even use the same model for a different earthquake? And that's the problem. We can't have a site-specific machine learning model to do our classification. So this is where post hoc explanations become useful. So we are not able to change how machine learning models are built. So what we try to do is try to explain later how things are behaving. The way we do it, and one of the ways we do it, is called as the Shapley value. Shapley value is trying to come up with unique contribution of each of those variables. So we want to find out how each of those variables contributed to the decision. So let's look at an example. There are 3 employees in the company, so tiny company, and we want to figure out what is the contribution from employee A, B, and C. So what is the contribution to the company if no one was there? The contribution is basically zero because no one is working, no work is done, the employee contribution is zero. Bring in employee A, they contribute 10, B contributes 20, C alone contributes 30, but you can put A and B together, B and C, A and C, and all of them together, they contribute to 100. Now we want to know in a team which contributes 100%, what is the individual contributions of A, B, and C? The way we do it is set up each of those in different combinations and try to calculate what is the value of A, value of B given A and B are working together, value of C given A, B, and C are working together. Do this for all sorts of possible combinations and then take an average of all their combination. That gives us individual values of A, B, and C contributing as a team together in making that decision. So although the individual contribution of A was only 10, you can see it has gone up to 30% in the overall company because they tend to work well with other parameters. So you can think of distance to the river might not be the only unique feature, but working it with peak ground acceleration and elevation, we might be able to explain things better. And this is what happens. So when you start to look at the Shapley values, here you see that it is correctly predicting a lateral spreading site, and it's saying the probability of lateral spreading is 90%. And we can now go ahead and ask the random forest, which was a collection of all the trees, which we couldn't explain before, why it made that decision. And here it says, oh, the distance to the river is only 0.026 kilometers away. So it's almost on the river. And that's the site that liquefied. And also a very high PGA value. Groundwater depth is 1.5 meters. All the lines that are red and moving towards the right. So anything above zero is lateral spreading. Anything below zero and going to the negative is working against. So red is working towards liquefaction and lateral spreading. Blue factors are working against lateral spreading. So this makes sense. So it looks good. And we can look at a case. We can look at someone's unmuted on Zoom. We can look at a case where there is no lateral spreading. And if you look there, you can see the groundwater depth is very deep. It's close to 3 meters. It's further away from the river, and things are starting to make sense. Why the probability of that particular case is only 7% for lateral spreading. Does that mean now I can go ahead and use it for different sites? Like, let's hold our horses, see where things can potentially go wrong. So this is a case where the random forest, which was accurate more than 85% of the time, and this is what it says now. It says it is incorrectly predicting there will be no lateral spreading. And when we asked it why, it said, oh, because you have a very high PGA of 0.554 G. And if you have a very high peak ground acceleration, that's more likely to lateral spread than not lateral spread. So this is completely counterintuitive to what we've been taught in our earthquake classes. And even worse, it says when there is low PGA, it says it's very likely to lateral spread. So the model, although accurate, 85% of the time predicted the Christchurch lateral spreading cases almost very well, did actually learn something bad. So we can't just use the models because they are accurate. We want to be able to explain them and see why it learned the bad thing. And most often, it's because the data had an inherent bias. And in this case, when we plotted the peak ground acceleration, I drew a horizontal line to say anything above that line is lateral spreading, anything below it is no lateral spreading. And you can see it's not a nice linear or a straight line relationship, but it is a complex set of different factors. But here we see any high peak ground acceleration over 0.5 G is causing it to have no lateral spreading. Thank you. And we want to figure out where this particular data came from, because that is kind of influencing all our random forest decisions. And when we looked at it, and you can see that here, close to the southeast region where we have high PGAs, we have very few data points, but these data points kind of control and say there is no lateral spreading in that region. And because of that, the model ended up learning something really incorrect. And if we don't have this explanation and someone uses it, we might end up predicting incorrectly. So we want to be extremely careful when trying to use black box machine learning models because they can be dangerous, in this case, affect people's life. So how can we fix this problem? One way is, remember the star I put on the right top corner, is to build a model which are not black box. There are techniques called glass box models because they are fully interpretable. And one way to do it is using boosted trees, what we do here is we take each of those individual features, like distance to the river, peak ground acceleration, elevation, run through 10,000 classification algorithms, put them all in a graph because we understand graphs. We like to see graphs and see how the trend is. And then say anything above 0 is lateral spreading, below is no lateral spreading. And if I do the same thing for PGA, I can see that my data has a bias and says anything with high PGAs of 0.5G, it is predicting no lateral spreading. I can either cut off my model or bring the graph up because we know what the relationship should be and fix it so that we can come up with decent explanations. And that's what we end up doing here is this is a particular site where it is predicting no lateral spreading. It has 0.41G, and that's the reason why it ends up predicting no lateral spreading. So instead of building black box machine learning models, which are highly accurate, the glass box machine learning models are fully interpretable. You can look through the model, look at the graphs and say, this is how it's going to behave. The benefit is you don't even need to know a computer. Once you have all these graphs, you can do it manually. I wouldn't recommend doing manually, but more parameters you have, more cross-correlation you need to do. But the idea is you can go through the calculation and figure out what is happening. So this is where we need to be going in building fully interpretable models. The next topic I want to talk about is seismic imaging, or trying to do inverse problems, which is trying to guess what does the subsurface looks like given certain dispersion curves. So we're going to use convolutional neural network. This is one of the most widely used neural network for image classification and image generation. It's a deep learning model. It has a sequence of layers, and each of those layers does a specific task. So the most biggest or the popular example is given an input image, you want to guess what that number is. So it's going to be between 0 and 9. The interesting part of the neural network is the top layer, the first layer, will only see the edges. And the second layer might see curves, and the third layer might see gradients. So if you're trying to deduce someone's face, the first one will just see the boundary. The second layer might see eyes, and the third layer might see the contrast between eyes and noses. And that's how generally each layer works. And the deeper you go, the less information it has, and the more distilled the information gets. So we can use the same neural network and has two parts. One is the convolution, which operates on a grid or pixels of images and does a matrix multiplication and addition, and that's the convolution stage. And there's a pooling stage where you can either take the maximum value in a grid or the average value in the grid. So basically, these two operations get repeated thousands of times on each of those layers, and that's how the calculation works. So we can use this convolution networks to predict building damages. You can quickly see and tell me that the first building is undamaged, the last one is completely destroyed. Humans are built for this. We can do that very easily, but we have to give hundreds and thousands of images for the models and say, this one is undamaged, this is partially damaged, this is completely destroyed. Keep doing it over and over again until the machine learning model figures out, oh, this is an undamaged building. And then when it looks at this building, it can say that's a general collapse. So here's what we are going to be mean to AI and give it a landfill and go, what do you think that is? And the machine learning model most often will say, that's a general collapse. And it actually did predict general collapse. The model which was trained, which is one of the most popular classifying model, we did a transfer learning on it, and then it said that's a general collapse. You can look at it and say that's a landfill, but for the model, it's a general collapse because we constrained it to 3 categories: general collapse, partial collapse, or no collapse. So it's going to pick one of those 3. So I removed the constraint and said, you're free to take a guess. And it made a wild guess that these are ants, not anything to do with buildings. So how do we actually know that it's a general collapse? We know because we see the rubble, right? But how do we know the machine learning model actually learned that it is the rubble that is the collapse and not the sky? So whenever it sees a sky, it shouldn't go and predict that's a general collapse. There's a big myth that whenever there's a tank in an image in the US Army example, there was a big tank, and whenever they saw a sky or clouds, it predicted there's a tank in the image. So it can learn a completely wrong thing to predict something correctly. So we want to be able to open up the black box. One of the ways, I think there's a speaker later in the next sessions talking about GradCam, is to look at a heat map of where the machine learning model actually sees. So we can say what we see by saying, oh, we looked at the rubble, but for a machine learning model, we can ask it to give us a heat map to understand where it sees. And you can see that it saw mostly in the rubble region. At least it's not looking at the sky, so that's a good starting place. And we are going to use this post hoc explanation to come up with a neural network that can solve inverse problem. The big challenge in designing a neural network, I talked about convolution rail kernel sizes, is how big should my kernel sizes be? 3 by 3, 4 by 4, 2 by 2? How many layers should I have? What is my pooling? Max pooling or min pooling or average? All of these is not a science, it's an art. So you do a brute force and figure out when my solution will become accurate. And you keep doing this over and over until you get an accurate solution. So that's not a good way. We don't have any framework or structure to design a neural network. And that's still an open area in research and computer science. So what we're going to do is start off with a neural network, and then I'll go ahead and use explanation to come up with a way to say, how should we build neural networks going forward? So we're going to do an inverse problem. So usually we know, given a soil profile, we can figure out what the dispersion curves are. Here, we're going to start from the dispersion curve and try to guess what the soil profile looks like. So the dispersion curve is the input image, and I have here a 3-layer convolution network which predicts the subsurface image. In case you're interested in figuring out how well we were predicting, so these are the true synthetic models we generated, and these were the predictions, and we had mean absolute percentage error. That's how bad our errors were. They were usually below 10 to 12%. And the other index which I want to introduce is called as the structural similarity index. Don't just use an error because that is already used in computer science. That might not fit our geotechnical needs. So sometimes when you're generating images, we want to be able to say whether the overall picture looks representative. Does it look like a soil profile? So one way to do that is use an index called structural similarity. And you can see that the image with noise is less structurally similar compared to the image on the right, where it has been just added a constant value. So that's much more similar to the original image. So we want to be able to use these to identify boundaries between layers, rather than just take the average of all the errors in my pixels and then say it predicted correctly or not. Okay, so we want to design the neural network. How do we do that? The first thing we do is plot the mean absolute error versus number of training steps. And you can see that the training and validation goes down, or the mean absolute error goes down. And I can do it for different types of combinations. I can use 5-layer model or a 3-layer model, or use different kernel sizes. So out of these 4 combinations, I'm only showing 4, but you can do this for any number of combinations. You can see that the kernel size 3 by 3 and the deep architecture gives me the smallest error. Anything that gives us the smallest error, naturally, that's what we're going to choose, right? And let's see what happens when we put explanations to this. So what we're going to do now is look through and explain which region does the neural network actually sees from our input image. When we do that and compare a deep architecture, that is a 5-layer model, but the only difference is I'm using a 3 by 1 kernel versus 3 by 3 kernel, you can see that it roughly looks at the primary mode, but it also sees the heat map, also shows that it is looking at higher modes as well. But do you notice that something bad happening at the bottom? That's the region which we don't usually care about, but the machine learning model is trying to pick that up and try to use that in its prediction. So what about a shallower network? A shallower network, the 3-layer model, you can see it only predicts the primary mode. It only sees the primary mode as the important one. The 3x3 kernel doesn't do well. So the model which gave us the highest error of 12% is the one actually doing correctly in terms of physics. Whereas the model which gave us the least error, which is the 3x3 deep architecture, is looking at something else. So we can't really trust that model in terms of giving good solve profile once we start extrapolating outside our regions. So we've been always interested in what does the model see. So we want to go deeper and come up with ways of looking at what does each of those individual layers see. You can plot like saliency map or feature maps, but we came up with a different approach. We developed an approach where we can actually invert a neural network, and given an output, we can make it guess what the input is. And we can make it guess what is the input at different layers. So when we did this, and we have to solve it iteratively, so like a local search problem, we'll give it an initial guess, solve it iteratively at different layers, and you can see that the top layer kind of sees the original image. We are able to recover back almost the original image. And as you go deeper and deeper, you can see the information gets lost or information gets more condensed. But the good thing is the primary mode is still the most important thing which the neural network is now seeing. Now that we have an approach where we can actually make the neural network backwards, so given an input, we usually predict an output, but what we made is given an output, we can guess what the input is. Why am I trying to solve a forward inverse problem when I can just make it solve a forward problem, work iteratively, get what the inverse should be? So go back to our original science, make my CNN predict the forward problem correctly. So given an input image, we'll get the dispersion curve, iteratively solve. So just to show you that I didn't give it the correct solution, that's the initial guess it made. And then iteratively solve for a few thousand steps. It takes roughly about 40 seconds. It reconstructed the original image. So this allows us to look through the inverse problems in a completely different way, where you can use CNN to go forward and use a iterative approach to solve the inverse problem. Okay, so last bits is where I think the future of physics informed machine learning should go, is we shouldn't be try and replace all the knowledge we've gained so far, but use AI to help us predict new knowledge. So what can we do? There are machine learning models which are useful in making dynamic simulations. So I'm a simulation, numerical person. My reality is simulation. Just because the title says reality, it's not a real world, but it's a simulation from NPM. Here we are able to, there's a slight lag in the runout profiles, but you can see that the reality and what the graph network predicts are pretty similar. And the benefit is one takes 2.5 hours to run. The time is not shown here. The GNS only takes 20 seconds, including the warm-up time for GPU. So imagine running a simulation that takes months. We could probably do it in a few minutes. And it will be very, very close to what your numerical simulation actually does. But again, the same question happens. What if I have a different boundary condition? What if I have different solve properties? We can do all of those. So like the models you're seeing are the outputs for which the GNS model has never seen a boundary condition like that. So it is able to replicate what the physics should look like for a condition that is never seen. So GNS or graph network simulators are really powerful ways to model solve behavior. We've done water as well, and make it much more generalized so you can use it for wider applications. So instead of running one simulation, now we'll be able to run thousands of them, look at probabilistically what is most likely to happen. But I've been always fascinated by knowledge discovery with AI rather than just use AI and replace. why can't we derive physics out of just looking at AI? So we take a simple problem, billiards game, and we simulate each of those particles as nodes in a graph. And the interaction that happens is the information that gets exchanged in the messages. So if I'm able to reproduce the physics as close as the real world, then somewhere at some place, the AI must have learned the physics. At least that's the hope. So we went through statistically figuring out where the messages were, and we took the least standard deviation messages and run through symbolic regression to find out what the interaction law should be. So what was the interaction law? Here it's a simple Hookean dynamics. It's a linear spring, right? So you make your AI PhD student do the brute force grunt work. It's not that good yet, so it's currently just brute forcing its way through. And it came up with this table of potential equations. So here you can see that equation 8 is in bold, but that has the least error in comparing to predicting what the accuracy is. And that equation, you know it, is in a slightly different form, is written below. That is, 100 is actually my stiffness. It's the absolute value of the distance between two particles minus their radius. Or in general, that's a linear spring equation. So without knowing what the linear spring equation is, I was just observing the dynamics, make AI predict it, and be able to derive the actual equation. Future, we want to make sure that all the equations it derives are dimensionally correct, because at the moment it's doing 50-50, half of it is not dimensionally force. So we want to make sure that it's a force equation that it always generates, and that's an active area of research. We're currently working in known systems because we want to show that in known systems it works well, so that when we start solving unknown problems, we'll be able to discover new physics and new mechanics of behavior. So thank you very much.
So the next presentation is with Professor Adrian Rodriguez-Marek and Professor Mosen Zucker. Professor Adrian Rodriguez-Marek with Virginia Tech and Professor Mosen Zucker with Utah State University. So please, Mosen.
Mosen, you're on mute. So, good morning, and thank you, Jorge, for the invitation, and thank you to EERI for the invitation. I'm going to start off this presentation, but the work really has been conducted by Mosen. Mosen was a PhD student here at Virginia Tech, and he did this work, however, while he was doing a postdoc working with me at Virginia Tech. He's now a brand new assistant professor at Utah State University. This work was funded by PG&E, and Albert Kotke from PG&E worked intimately with us in developing this work. So consistent with who did most of this work, I will only give the introduction, the first couple of slides, and then I will pass on the presentation to Mosen. Next. So the outline of the presentation, I will give a brief introduction. I will pass on to Mosen. He will talk about site proxies. He will talk about the data-driven framework that was used in our work, and then the assessment of the resulting model, some work on sensitivity, and finally, some concluding statements. Next. So ground motion models are used to predict the distribution of the ground motion intensity measures of future earthquakes as a function of predictive variables. Those are variables that we can use for prediction that are grouped into functions of source variables, path variables, and site characteristics. You have here on the right-hand side, you have an illustration of this. We have parameters that control the source of the earthquake, the travel path from the source to the site, and once the waves get to the near surface, then we perform typically, or we have the effects of the local site conditions that we group as site effects. And typically, as geotechnical engineers, we do site response analysis to predict these effects. Ground motion models, however, they use simple proxies to predict what the site effects are. These proxies generally in modern ground motion models are the time average shear wave velocity over the top 30 meters of a profile, VS30, or the depth of shear wave velocity equal to 1 kilometer per second or 2.5 kilometers per second. However, these proxies are simple two parameters that try to represent a very complex phenomena that is site amplification. So none of these proxies can sufficiently account for the specific geological structure of a site or for all the complexities that are related to the site response phenomenon. So next, please. A viable solution is to improve our prediction of the site term by looking at different proxies. And one such candidate proxies are horizontal to vertical spectral ratios. Horizontal to vertical spectral ratios would be the ratios of ground motions in the horizontal direction, typically the average of two horizontal components divided by the vertical component. And there has been a lot of work that has been done in the past showing that these proxies in this measure, horizontal to vertical spectral ratios, are related to site amplification, or the theoretical underpinning varies, whether it is the noise or the strong motion spectra. So these proxies we know from this past work they can describe several aspects of these characteristics. One is the site fundamental frequency, which is generally universally accepted that the peak of the horizontal to vertical spectral ratio corresponds to the site period. But in some people argue also that the shape of the horizontal to vertical spectra is similar to the shape of the transfer function. Now, horizontal to vertical spectral ratios come in different colors. We can compute these from earthquake recordings, and we label these EHVSR. We can compute them from microtremors. We label those MHVSR. The advantage of MHVSR, so those computed from noise or from ambient vibration, is that it provides a cost-effective alternative to conventional proxies, because you can actually place an instrument at any site, record for an hour, and you have the proxy rather than going through the process of measuring VS30. Next. Now, selecting the efficient proxies is not a straightforward process. Most of the development of ground motion models use scalar proxies, simply just one value. VS30 has been the typical value. However, using data-driven proxies or data-driven frameworks allows for a more flexible solution, because you can do it in an automated fashion, and you can deal with high-dimensional data. So we are not constrained to using scalar or simple low-order vector proxies, but we can use large proxies. And what we do in this work is to present a data-driven approach where the proxies that we are using are horizontal to vertical spectral ratios obtained from earthquake recording. And the objective is to predict the site term in ground motion models. Okay, so in order to minimize our uncertainties in prediction. So next, the ground motion data are obtained from a database of the KickNet network. And we use a Fourier amplitude spectrum that was a Fourier-based ground motion model that was developed by a previous PhD student of mine, Madhi Bahrampuri. This model is a typical model postulated in the Fourier domain, where we have a magnitude term, a path term, and we have, next, please, we have terms that are function of VS30, Z1, and ZTOR that are predictions of site effects. ZTOR arguably is I would rephrase this, sorry. ZTOR is more of a prediction of source, but VS30 and Z1 are prediction of site effects at a given station. Okay, so our objective now is, can we improve on these predictions using HVSR? Next, please. If we look at the delta S2S in this equation, this delta S2S represents the average residual at the site once the prediction has been corrected for all the other components, so source, path, and the side terms as predicted by VS30 and Z1.0. So later on, we'll refer to this as a side term. If we put together FVS30, FZ1, and delta S2S, this whole term is what we'll term the transfer function, because it constitutes in the frequency domain the difference between the response at the given station, station S, and the reference condition for the ground motion model. So in the remainder of the go ahead, next please. In the remainder of the talk, Mohsen will focus on on the use of machine learning tools to predict either the full transfer function, that's the difference between recordings and the average reference condition for the network, or particularly the side term noise, the difference that the particularities of side response that are not captured by the ground motion model. One last observation is that the side-to-side variability of the side term is a measure of how well the ground motion model predicts side response. Therefore, we will use this measure to evaluate how well the ground motion model works. So the lower this measure is, which we call phi-S2S, the better our prediction of the side effects are. With this, I will pass this presentation to Mohsen.
Oh, thank you, Adrian. So what is the input of the machine learning models? There are two types of input. The first one is the HVSR spectrum at frequencies between 0.1 to 30 hertz. And the second type is proxies derived from the HVSR spectrum, such as amplitude and frequency of the first peak or predominant peak, as well as their prominence and weights. It is believed that these proxies can summarize or represent certain aspects of the HVSR spectrum. This data is obtained by an open source database compiled by Zhu et al. And as I will show in the next slides, the machine learning algorithms could examine the different sizes of input features vectors from single value, such as HVSR amplitude at any given frequency, to entire input space comprising the entire HVSR spectrum and all the derivative proxies. Now, the machine learning pipeline starts by reading the input features and target data, splitting the data set into training, which is about 80% of the total data, and testing, which is about 20% of the total data, and applying a variety of feature-based selections ranging from filter, embedded, and wrapper methods to pre-select a subset of this input space based on data associations. Next, a machine learning algorithm is chosen and paired with the selected features to be tuned based on a hypertuning module. The hypertuning module uses a sequence of randomized search which identified the hyperparameters ranges, and also a grid search which find the optimal value in those ranges. At each training iteration, a threefold cross-validation is performed to ensure that in the training, the machine learning is not picking up the noise in the training data set. Finally, the tuned models are applied to the fresh data of the test set, and their accuracy is measured based on adjusted R-square, root mean squared error, and also the standard deviation of the prediction residual, or phi-S2S. Now, before making any machine learning model, a data exploratory analysis is always a good idea to make sure that we have good insights about how the machine learning model should perform. Here, this data exploratory analysis applies statistical metrics to select features. We use correlation metrics such as Pearson and Spearman, and also mutual gain to evaluate the transfer function and HVSR proxies association. The result shows that transfer function is well correlated to HVSR with similar frequency. Also, transfer function is correlated to a larger number of HVSR frequencies at low frequency range. The same observation can be made with other data association metrics such as mutual gain. And to better understand this data association, the correlation structure is fed into a clustering algorithm. And that clustering algorithm showed us that there are three areas of distinct relationship between transfer function and HVSR. Below 2 Hz, between 2 to 7 Hz, and above 8 Hz. Also, such a strong data association in those regions is a good sign that machine learning models would be effective to predict transfer function based on HVSR. We also employed an embedded method to evaluate the data association between transfer function and HVSR proxies. Some machine learning algorithms have built-in feature selection processes in their algorithms. And a prominent example is regularization technique. And in particular, are either lasso regression or elastic net. Now here I'm just showing the lasso regression. And a lasso regression minimizes a two-term objective, as shown here, where the second term is a penalty term and controls the number of predictors. The lasso regression selects similar predictors, as you can see here, as the one that was showed in the correlation structures from the other data association metrics. And you can see this better here at the diagonal portion of the HVSR spectrum, which kind of shows that HVSR at the same frequency of the transfer function, then these two data are better correlated. Also, we can see that F0 and A0 are selected for transfer function for mid-range frequencies. Now, after some exploratory analysis of features, we use wrapper-based feature selection algorithms to automate feature selection over the entire input space for different algorithms, because we needed to make a lot of trial and errors of different algorithms with different input spaces. Here, wrapper-based methods explore feature space by examining models developed based on various input combinations for a given machine learning algorithm. So basically, the results are specific to the algorithm. Now, what we did was to employ a two-segmented feature selection workflow. In the first step, a recursive feature elimination method is applied to find the best input subsets with K features, where K can be 1, which means a subset with one single optimum predictor, to N, which is the entire input space and all the predictors. Now, recursive feature elimination, or RFE, recursively trains a machine learning algorithm with all features, then evaluates features' importance, and removes less important features to achieve the desired number of features. After we do this, we can get like N number of subsets, all of them having different sizes, but all of them being optimum with the size given. And if we plot the model accuracy in terms of, for example, any metric, let's say root mean squared error, versus the number of predictors, we can see a curve like the right plot. In a manual model development, the analyst will select the number of predictors by accepting an accuracy cutoff, meaning that after a certain number of predictors, there is no significant change in model accuracy. Now, step 2 of our algorithm mimics this by searching along the RMSE of the resultant machine learning models on the training sets and find the optimum number of predictors, which is like the optimum K, where the accuracy of the resulting model cannot be further reduced by alpha% with respect to the previous lowest point. Therefore, this alpha is a subjective value that controls the trade-off between model accuracy and number of features. And as I will show in the next slides, sensitivity on what is the optimum value of alpha has been performed as well. Now, there are various machine learning algorithms, and here we are comparing 3 models as representative of 3 machine learning classes: multiple linear regression, support vector machines, and random forests. Multiple linear regression assumes that the response variable is linearly related to several variables. So multiple linear regressions, or MLR, are straightforward and clear. However, they usually show poor performance for highly nonlinear problems, where they compensate by requiring a larger number of predictors to identify those regions and do the mapping. Now, support vector machine is usually formulated to find the optimal hyperplane that separates the transformed input data by a margin of error. And support vector machines, or SVM, efficiently can handle nonlinearity through their kernel function. And also they can handle high dimensionality, but they're usually very challenging to interpret. So there is a bit of an interpretability issues. And finally, random forest, they aggregate predictions from several decision trees where each tree uses a criterion to recursively split the data based on like some indexes like Gini index. So we can have input feature ranges that improve the homogeneity in each partition. And random forests can deal with overfitting and data imbalance automatically because of how their algorithm is established. But in contrast, they can show poorer performance for regression than classification problems. And also, their performance gets worse when you are looking at new data beyond what the algorithm was trained on. Now, after all this, we trained those models with our input space with the best feature sets, and we got these results. So the results showed that data-driven models with HVSR proxies provide lower site-to-site variability than the conventional grand motion model or the baseline grand motion model. The best performing data-driven model, which is the support vector machine, showed an average of 24.1% and up to 50% lower site-to-site variability or PS2S than the baseline grand motion model, where the difference is more significant at lower frequencies. Now remember, that is where we know that we have better correlation. So this confirms our intuition about the data based on the data exploratory analysis. In addition, random forest showed the lowest performance by only improving PS2S on an average of 11.1%. And when we look at the adjusted R-square of these models, as you can see on the right plot, again, we can see that support vector machines provide the highest accuracy, where the adjusted R-square is on average 10 and 23% larger than multiple linear regression and random forest models. Now, overall, all models favor, when we look at the features, they favor the vector of HVSR spectrum over derivative proxies. Among derivative proxies, F0 is more frequently selected in combination with other HVSR frequencies. Also, we can see support vector machine and random forest select fewer parameters to do the mapping and the prediction. So basically, this is because of their ability to consider nonlinearity, whereas multiple linear regression to achieve the same accuracy needed to compensate by almost adopting the entire HVSR spectrum. And you can see that for support vector machines and random forest, again, we see that diagonal pattern, which means that the transfer function at the same frequency of the HVSR, that is where these two are better correlated and can help for the prediction. Now, how about the actual prediction? Here on the left, on this plot, we can see the predicted versus observed transfer function, where at each point transfer function is averaged over the entire frequency range for that site. First, we can see all machine learning models have reasonable accuracy, where multiple linear regression and random forest have a similar accuracy as the baseline model, which is an adjusted R-square in the realm of 0.56 to 58. Again, support vector machines outperform other algorithms and provide better prediction. The adjusted R-square is about 14% higher than the baseline model. Now, besides the median prediction, we want to look at how we can account for the variability in prediction of these machine learning models. And this plot compares both median and the range of prediction. And we can see while the median prediction of machine learning models are often very close to the actual observed data, which is the data in the test set. However, the machine learning model's ability to consider the transfer function variability varies a lot between these algorithms. Where, again, support vector machines outperform multiple linear regression and random forest in capturing the actual transfer function interquartile range. But one thing that I want to emphasize is that, nevertheless, all machine learning models cannot represent the extreme transfer function values. And these are the values that falls outside of 1.5 times the interquartile range. So this is some sort of shortcoming that we can see in these models. What is the prediction compared to physical trends? Here we're looking at machine learning average prediction versus site condition proxies of VS30 and Z1. And we can see that the average transfer function decreases for sites with higher VS30 and increases for larger Z1 values, which is similar to the baseline ground motion model. And these are the trends that we expect. Now, remember, the baseline ground motion model has physics-based term, right? It's a conventional ground motion model. But these machine learning models were not explicitly modeled to account for this relationship. And this observation reinforces how machine learning models are able to extract the underlying relationship and somehow hint at an implicit relationship between HVSR, VS30, and Z1. Now, during model development, we perform a series of sensitivity assessments on the workflow choices because data-driven models are often very sensitive to the kind of assumptions you make. And the first thing that we did the sensitivity was we measured the sensitivity of our machine learning models to alpha choice. And we observed that while decreasing alpha increases model accuracy, there is a certain threshold that after that, alpha does not tangibly impact the model accuracy. This means that basically we can find an optimal alpha through trial and error, where we can set that as our threshold and have the best models. Now, as shown here, model results are quite similar for alpha values below 20%. For multiple linear regression, the average difference between VS2S and adjusted R-square of models derived based on alpha values of 10 and 15% are only 0.7% and 0.3%. Whereas the difference for SVM models developed for the same alpha changes to 2 and 6%. And this is another reason that we can say it is feasible to find the optimum alpha in the workflow. Now, we also perform sensitivity assessments to evaluate machine learning models' accuracy if only derivative proxies are used instead of the suggested features that the workflow decided. And here you can see the multiple linear regression and support vector machine models that were retrained to only use derivative proxies. And those are proxies like F0, A0, and not using the HVSR spectrum raw data. They are used as the input in the workflow, and then we went through the whole training of these machine learning models. Now, the results showed that these new machine learning models provide either similar or lower accuracy than the baseline ground motion model. For example, on average, support vector machines with only derivative proxies showed about 7% higher VS2S than the baseline ground motion model. Now, it should be noted that while these models are not as useful as the ones with the optimal feature sets, they still show moderate adjusted R-square. And the adjusted R-square is positive over a lot of the frequency range, which means that these derivative proxies can partially explain the variability in transfer function, but they're not as good as the selected features that the data-driven workflow suggested for us. Lastly, we wanted to see if the recursive feature selection algorithm has an impact on the selected features. So we tried other wrapper-based methods. For example, we tried forward and backward selection as part of our workflow. And first thing, we see that the results are very similar. This shows that the workflow is robust against such choices. For example, you can see here that the multiple linear regression, the final VS2S from the model developed by forward selection is about 3% smaller than the multiple linear regression model developed by RFE. This difference falls to 0.05% for support vector machines. So the linear models are usually more sensitive to the selected predictors than the nonlinear models here. Now, one thing that I want to mention here is that our discussion so far showed that earthquake-related HVSR can substitute VS30 and Z1, but does it provide additional information than these proxies? Now, to evaluate this hypothesis, the multiple linear regression support vector machines were retrained to directly predict site term. And by site term, I mean delta S2S here. And this site term is the residual from a VS30 Z1 model, or baseline ground motion model, which means that it is already detrended for them. And as you can see in this plot, we can see both models, except for multiple linear regression at frequencies around 2 Hz, consistently show a positive R-square, indicating that there is an ability to explain variability in site term. These models have lower predictive power than the case where we were predicting the whole transfer function. And when you combine these two facts, having a positive adjusted R-square to explain delta S to S, but having lower predictive power, we can see that these earthquake related HVSR have additional information than VS30 and Z1, but the amount of new information is limited. Now, in both models, fewer parameters are selected compared to the case where we were predicting transfer function, indicating that fewer earthquake-related HVSR proxies are informative enough to predict the site term directly. For example, support vector machine now only uses HVSR at a similar frequency to the site term for the frequency between 2 to 11 Hz. And this observation showed that HVSR frequencies at the same frequency of the site of the transfer function or the site term are essential to explain those variabilities, and they contain information that is not accessible to other common site condition proxies such as VS30 and Z1. Now with this, I would like to have our presentation key points. First thing, all data association measures such as Pearson correlation indicate that the transfer function is more correlated to HVSR at the same frequencies, especially at the lower frequency range. We saw that using only earthquake-related HVSR proxies, all machine learning models resulted in lower site-to-site variability or VS2S than the conventional ground motion model using VS30 and Z1. And among the different machine learning models used, support vector machines provided the highest accuracy, where average VS2S was about 24% lower than the baseline ground motion model. Also, we saw that the average predicted transfer function of random forest and multiple linear regression was close to the baseline, where again, support vector machines provided 14% higher adjusted R-square. We also see that the linear model, the multiple linear regression, recorded almost the entire HVSR spectrum to maintain similar accuracy as the nonlinear machine learning models. And one important observation was that the advantage of machine learning models over the baseline ground motion model is more pronounced at lower frequency below 2 Hz. That's where we also saw the best correlation. And all models, machine learning, baseline ground motion, show lower accuracy at frequencies above 2 Hz. In many cases, machine learning models favor the vector of HVSR frequencies over derivative proxies. And among the derivative proxies, F0 was found to be the most important one. And lastly, we can see that earthquake-related HVSR proxies provide additional information than VS30 and Z1 and might be able to substitute them in a ground motion model. With that, I just wanted to finish the presentation. Would like to invite you to keep an eye out for a publication at Bulletin of Seismological Society of America, which hopefully will be published soon. And I also would like to thank Dr. Bahrampuri, Dr. Zhu, Dr. Faber-Scotten, Dr. Kota, and Dr. Cox for their suggestive comments, feedbacks, and their help in data assimilation. And also, I want to acknowledge the funding provided for this work by PGI.
Next presentation is by Professor Scott Brandenberg. Okay. Professor Scott Brandenberg from UCLA. Please.
All right, great. Thank you very much, Jorge. It's an honor to be here at this colloquium honoring Professor Ishihara. I'm a big fan of the work that he's done, had a very distinguished career. So it's wonderful to be here to present. I'd like to thank the committee for honoring him in this way with the colloquium. So when Jorge invited me to be here to talk about machine learning and AI, I said, I don't really do that. I do a little bit, but certainly not like the presentations we've seen so far today. But I said, can I come talk about data? He said, yeah, sure. And so this is the super exciting part of today where we get to hear about data. It's like kind of the nuts and bolts part of AI. Actually, data scientists spend over 80% of their time working with data, not doing training of algorithms and kind of the fun stuff that comes at the end. So this is a really important part of facilitating AI and machine learning. And I'm going to present today on ground motion and liquefaction. So I'm covering topics that were already covered in the previous two presentations. And I'll talk quite a bit about our next generation liquefaction project. And you can see well, I guess you can't see the list of sponsors up there at the top. This is the Nuclear Regulatory Commission and Bureau of Reclamation, big program that we've been working on collaboratively for quite a few years now. So I'll talk first a little bit about databases, because when people in civil engineering talk about databases, they usually don't actually mean databases. They mean file repositories. And it's important for us to understand what a relational database is, because I think that they have a lot of benefit when it comes to doing this kind of data science. And I'll talk a bit about a ground motion database that we've put together that's publicly accessible through an API. That's an application programming interface that all of you can use. It still has a few bugs in it that we're working out, but just using a web browser, you can download data from our ground motion database. We have 35,000 or so 3-component records in there, from all in California, but I think that that's going to expand. And then I'll talk about the next generation liquefaction project. This is a big publicly accessible relational database where you can go use our interface, or you can query it directly using SQL queries through DesignSafe at University of Texas. And then I'll provide some examples where we actually have done some machine learning techniques on some of the data that we have. So most of it will be on data. So let's start with database. First, a common definition of database, one that I use still to this day, is a collection of files. So you might say, hey, would you send me your database, right? And the other person say, sure, it's too big to email. I mean, I'm sure we've all had these interactions before, right? I'll post it to Box. You can go download it. Of course, a better thing would be to publish your data, right? Make it available in DesignSafe or a repository system where you can get a DOI and it's citable and it's always there, and say, oh, sure, I don't need to send it to you. Just go to this link and you can download it for yourself. I think that to facilitate machine learning, we all have to do a better job publishing our data, making it available for everyone else to use, because the name of the game is data integration now. It's kind of old fashioned to think I'm going to collect my own data set, do my own analysis of my own data set only, and that's it, and then I'll publish it. That's not the way the world is working right now. So it's important to get the data out there. So if you go to DesignSafe, you might see something like this. It looks like a publication. It has these DOIs. You can cite it just like the paper. And then there's version control. So if you change the data, you can go in there later and update it. And so this is great. Ellen Ratchey is the PI of that. Quite a few of us here, I think, are involved in the project. So hopefully it's useful for everybody here. There are some downsides to file repositories. Okay, it's great sharing data. That's a wonderful thing to do. But let's say that you have a file that's 5 gigabytes, right? And somebody has to go download that whole file, but they only want a little piece of that file. I think this happens all the time too, right? Now we have to figure out how to open this. Have you ever tried to open a 5 gigabyte file in Excel? Right? Excel is the program that a lot of us use to work with data. It's very limited. So then different people might also format their data differently. They do similar projects using even the same equipment facility, and their data set is formatted with different column headings. You have to go in and interpret what do all those column headings mean. Sometimes it's the same thing, but they put them in there in different ways. So anyway, this file repository thing is great, but that brings us to a database, which is a structured set of information that's queryable. So a relational database is defined by an organizational structure called a schema. So all of the columns are predefined and they have a specific meaning. And then tables are related to each other by keys. So there would be a number, usually it's an integer in one table that would identify a record in another table and tie those two things together. And having different tables allows us to avoid repetition and ensure data integrity. So it's a better way of storing data than to put everything in a flat file format from the outset. So databases are accessed using structured query language, SQL, and then there's MySQL, PostgreSQL, SQLite, all kinds of different database management systems that you can use to store your information and write these queries. So here's an example flat file. We've been talking about ground motion. So this is, ground motion data. You may all be familiar with downloading a flat file and getting the data, right? It has the earthquake magnitude, location, and every row is a separate ground motion. Then it has the response spectrum in there and everything. This is a much simpler table. where we have just the event name. And these are Westwood and Hollywood, so very LA names that I've come up with here, totally fictitious data. Magnitude, epicenter information, and then there's station name and VS30, distance, and PGA. And so that's all in there, and that's fine. But we really have three different kinds of information that are being stored here. We have our apples. Those are the events, right? So magnitude, epicentral latitude, and longitude. Notice there's repeated information here, right? What if somebody at the USGS comes along and says, oh, the magnitude wasn't 6.3. Upon further review, it was actually 6.4. If you've stored this in a flat file, you have to go in and change a whole bunch of numbers, and there's a good chance that you'll forget to change one of them. And then it's like, well, what is the magnitude? There's inconsistencies. So this is a downside of this kind of flat file structure. Then we have our oranges. These are the stations, so the Factor building and the Santa Monica Courthouse, each their own BS30. And then there's the ground motions that are associated with that station for that event. So if we were to do this in a relational database instead, we would divide it up into three tables. The apples, the oranges, and bananas would all be separate. And notice the keys, right? So every record in each table has to have a primary key shown in gold. That's just a unique identifier for that row or that record. And then in the motion table, there's two foreign keys. The motion ID is the primary key, and you tie it to a particular event and a particular station. And now if the USGS changes the magnitude of that event, there's only one place where you have to change it, and it's done, right? So it's a much more straightforward way of maintaining the data. And then there are queries, right? So the database, lives on a server somewhere, and you have to query it to get the information out. And so let's say you wanted to reconstruct a flat file now that you've separated the data into all these different tables. The flat file is a really useful product if you want to share it with people. So you just write a query, and that query is shown here. Select star. The star is actually not great. You should probably put in the fields that you want to get out of the database, but I did star because I was running out of room. That just means get everything. And then there's an inner join statement, which will take the intersection of the two tables where they share a common key. So that query would reproduce this table, right? So we have our flat file back. And so a good way to do it is to store the data in the database, and on command, when a user pushes a button, serve the flat file to them if they request it. And now maybe you don't need everything, right? You don't need to know the latitude and longitude of the epicenter or something like that. You can just ask for the data you need for your particular analysis, and you don't have to download this huge file to work with. So I'll talk a little bit about our own ground motion database for California and the API that we're continuing to debug and work on. The motivation for this is that we have a lot of students at UCLA who've been processing ground motion records. And a lot of the time they've been using the peer processing code, which is written in R. And, there's a lot of details that go into processing ground motion records. You can't just use the raw recorded record. It has to be filtered and baseline corrected before computing a response spectrum and intensity measures and things like that. And more recently, we've been using an automated code called GM Process. It's developed by the US Geological Survey, and that's at Hearn et al. Reference. And the data that we have include the time series. So we're actually storing time series in our database instead of in files, which is kind of a different way of thinking about it, right? We're usually thinking in terms of files. Now this is a JSON string that's stored inside of a table in the database. So it's up to about 10 gigabytes now. If you wanted to download the whole thing, you could do it, but you're not going to be able to open it up in Excel or some tool that we're used to working with. We also store all of the processing parameters. What was the corner frequency that was selected, to cut off the low frequency part of the record. We have intensity measures, PGA, PGV, and then all the response spectra. We have smooth Fourier spectra in the database as well. I think so far we have about 35,000 records, 3-component records. And then the other motivation, just kind of selfishly, we want to share it with the community, but it's also great for our own students to be sharing information with each other. It's kind of surprising how people can sit in the same room, have some information that they could really benefit each other, and they don't talk about it, right? So putting it all in a local shared system is really good. And then we've created this API because, I showed that example query. Our database gets to be a little bit complicated. And for us to expect users to know how to write those queries, that's kind of a high bar, right? You'd have to learn some database language and stuff like that. So the API, you just put in some URL parameters and it gives you the data that you want, that you ask for. Here's an example that shows where all of our data are. So those beach balls are all of our events. And the reason that we've developed this particular slide for looking at non-ergodic site and path effects. And so we've gone down to pretty small magnitudes because for non-ergodic site effects, at least for the linear part of the site response, you can use small magnitude earthquakes, right, to see does the site systematically shake harder or less hard than the ground motion models predict. And so you can see here the red is the additional data and the blue is what was in NGA West 2 for California. So we've added quite a bit of information here. One thing to keep in mind is that there is a fall off with natural period. So because we're cutting off certain frequencies, the long period spectral accelerations are sometimes influenced by the filtering. And so we suggest you have to cut those off. But we store the full thing, the full spectrum is in the database. And here's a screenshot of GM process. So this is a code written by the USGS. It uses Python to interface with various ground motion networks to get the ground motion parameters in, and then it facilitates automated processing. And we've contributed some code to this to do the corner frequency selection, but it uses OBSPy. There's a whole bunch of good stuff in there to facilitate ground motion processing. Sorry, I'm getting feedback. Sorry. Is it good? Okay. So we don't want to trust GM process just to process the records automatically and just say, oh, it's good, right? Nobody's ever looked at it. So we developed a GUI also where we can load up those ground motions, look at them, make sure the corner frequencies are good. Sometimes, this is a good record, but in the bottom left, you'll see all these wobbles in the displacement if we haven't done a good job with the filtering. And then this is a graph network map of our database. So the nodes are the tables and the edges are join statements. So left joins in this case. And a complicated thing is when a user puts in the URL, like 2 different tables that they want out of the database, we can't just directly join tables that don't have keys in common. So we have to figure out what's the pathway to go through this database and what tables does the user actually want. So that's why we made this little graph network, and it has algorithms to find shortest pathways and stuff like that. But you can see at the far left, we have the Fourier spectra, intensity measure, response spectra, time series metadata, and then time series data, and it goes off to the right. We even have some polygons in there that will delineate regions and things like that in GeoJSON format. And then here's what our web interface looks like. So uclageo.com/GM database API index.php/flat file. And it will give you a default set of parameters if you don't put them in, but you can also add query strings after flat file using question mark and signs and build it up. You've all probably seen these URLs, like when you're online shopping, it'll keep track of different stuff that you're looking for, shoes or whatever, and that'll be like shoes up there in the URL, right? So our version of shoes would be response spectrum instead, right? And we don't have cookies that keep track of what you're looking at, and you're not going to see ads when you go to another website for ground motion data. Okay, if you're interested in it, send me an email. I'm happy to give you information if you want more. So I'll move on now to talking about the NGL database. So the next generation liquefaction project has been going on for quite a while now. Where our goal is to advance the state of the art in liquefaction research and to develop a consensus approach within the community to develop probabilistic frameworks for liquefaction triggering and consequences. One of the big aspects of NGL is that we've developed this database. It's a public resource available to everybody. You can go there and download liquefaction, boring logs, CPT data, observations, photographs, maps, stuff like that. It's all together in one place. And then there's also a modeling effort that we're going through right now to actually use all the data in the database. And there's some supporting studies and other aspects of the project as well. So here's, you can get to it by going to nextgenerationliquefaction.org. NGL.org was already taken by some kind of natural gas company, so we couldn't get that one. We weren't going to try and buy that URL from them. So if you go there, you'll see all the beach balls that are the earthquakes, and then you can click on individual locations, and it'll kind of explode out and show you CPT data, boring logs, whatever information you want. And so here's some of the example of the contents of the database. This one's from the 1989 Loma Prieta earthquake. So there are sites, and if you click on a site, you might see a map. This is Moss Landing, which had some liquefaction and lateral spreading during the earthquake. And then you can see the boring logs in there, photographs like this. We even have some co-located ground motion records where liquefaction manifestation was observed at the surface. And you can start to look at those ground motion records to identify the timing of liquefaction, because there's a sudden fall off in the frequency content of the ground motion, as shown in that spectrogram there on the bottom. That was done by Mike Greenfield and Steve Kramer. And more recently, we have laboratory tests. So there's direct simple shear, triaxial, a lot of index tests, plasticity, and things like that. And some of the sites have a lot of data. So this is the Moss Landing site. It's kind of a sand spit, and you can see, all these boreholes and CPTs, and the black pins are observations. So these are sites where liquefaction was observed to have happened or was observed to have not happened, right? So the observations of no liquefaction are really important, because we need to try and separate liquefaction from no liquefaction. And then you can look at it in the map view as well. This is the approach to the Bay Bridge. I'll skip through this. You can plot the CPT data also on the fly and look at it. So these plots are not prepared ahead of time. You push the plot button and it queries the database and makes the plot. So if the data changes, it doesn't get out of date. This is what's in the database so far. We have 900 and some CPT soundings and boreholes. We have surface wave measurements, although not that many of them yet. We have some invasive shear wave velocity profiles, so suspension logs, downhole CPT, stuff like that. About 700 observations of liquefaction manifestation and about 500 non-liquefaction observations. So that part is probably biased, right? If we think about it, liquefaction happens only in a few local spots, unless you're in Christchurch, where it tended to happen everywhere. So I think we're biased toward liquefaction, yes, observations, because that's much more fun to go look at when you're traveling across the world to go on a reconnaissance mission, right? Take a photo of a sand boil. And then we do have this review process too. So every piece of information is reviewed twice. The website that we have will allow you to go download CSV files that contain the data, but you can't develop a workflow using our web tool, right? So we do have an interact with data button there, and you can go see our schema, which is here. So this is a list of all the tables. I think we have 60 something different tables in the database. The computer scientist who helped us write the interface said it's the most complicated database he's ever worked on. So we own that record for him. So in order to facilitate a deeper development of workflows, we have copied the database to DesignSafe. It gets copied every day. And when it's in DesignSafe, you can now open up a Jupyter notebook there and go and write your own queries and pull out whatever data you want. And then that's using Python. Once you're in Python, there's all the machine learning tools available already, so you can do your analysis right there in the same location too. And so this is a use case documentation. So we have some example notebooks that are all documented in DesignSafe. If you go to DesignSafe and go to the workspace and then use cases, you'll find this. It's only like, 2 clicks away or something like that. And I'll just walk you through one of the example problems. This is example queries. So right in the second cell there, you can see an import DesignSafe_db.ngl command. So that's a pip installable package that allows you to connect to the database. It provides the password and username and all that stuff. And then I wrote a command there. SQL is the variable name, and it's just a string, right? Select star from site. So I'm getting everything from our site table, and then reading it directly into a pandas data frame. And you can see all the data right there in the window, and it's just, they're kind of ready if we wanted to do future additional processing. And then here's one where we can get out some CPT data. So I'm going to do this for the wildlife liquefaction array, which is down in the Imperial Valley. And this one is a little more complicated, right? The command is now 5 lines, and I'm adding to it with each line. So it's a much longer string, and we're doing some inner joins because, as you can see, we had to go through different tables, right? And you have to join those tables together so that the query knows what information to return. And there you can see some observations, whether or not there was surface evidence of liquefaction at these sites and so forth. And then here you can get out the cone penetration test data too. So the actual cone data is in the database also. You don't have to just like point to a separate file that is not uniformly processed or whatever. It's all there in the database. You can just query it. So I'll talk now briefly about some of the work we've been doing with these data. I'll focus on the NGL data. So the first thing we've been working on is a layer detection algorithm for the cone tests. So as I showed, we have 900 and some CPT soundings in our database. The way that CPT soundings are usually interpreted is that a geologist or an engineer will look at it and go and identify strata, right? So here's a layer that has these properties. And then there's little transition layers in between where we know that the cone will average properties and can give you some false readings sometimes and stuff like that. And it's a little bit tedious to go through and do that and then extract information. And the way liquefaction has traditionally been done is we'll identify one critical layer from this profile, extract its cone tip resistance, for example, and then plot it on the triggering curve and see if that's going to trigger or not for a given earthquake. But other layers may also contribute, right? So there's huge benefit in doing this in an automated way that will store information for all of the different strata for us. So we started looking into an unsupervised machine learning technique called clustering to try and identify different groups of soils that kind of have similar properties. And we use k-means and Gaussian mixture models at first. And this is kind of how we do soil behavior type, right? So based on maybe the plots are a little different when we assign a soil behavior type to the soil, but if it's silty sand, it would have a certain combination of I sub C and tip resistance. So we tried to do that here, and it didn't work very well for us because it doesn't keep track of the fact that the layers that we want are vertically continuous, right? So it'll cluster things from different depths together, and maybe those are similar soils, but they're not part of the same stratum. So we switched to an agglomerative clustering method that uses a nearest neighbor matrix. So super simple matrix in our case, we constrained every single data point to belong to the same cluster, either as the data point above it or below it, but no other data points, right? So you can have a layer boundary and they don't belong to the same cluster, but they can't belong to a cluster that's from a faraway neighbor unless that's also part of the same stratum. And so this is showing some results on the right side, which look pretty promising, right? We've now identified continuous strata kind of the way that I would do it by judgment. So our approach here is to try and tune the machine learning to match our judgment. And in doing that, we realize like, how good is our judgment anyway, right? So we question ourselves and it's like, oh man, maybe the algorithm's actually better than me at doing this because I might be tired on a Friday or something like that. One thing we found though was that we were using a method called the elbow method. And that's where you look at the point of maximum curvature on this cost function on the bottom left to try and assign the number of clusters that you're going to use. And that didn't work well at all. So what we found was that very deep cone penetration tests would end up having many fewer clusters per meter, right? So the layer thicknesses on average were much bigger if the cone profile was deep compared to if it was shallow. And that shouldn't happen, right? The number of layers should depend on the stratigraphy and the natural variability. So we combined it with a new cost function that kind of penalizes layer thicknesses that get below 0.5 meter or something like that. And now it's unbiased with respect to depth. And then let's see, I'm supposed to be done at 9:45, right? All right, so I have some time to go through this. This is good. I don't actually have 150 slides. So, so I wanted to show this because, one thing we found, well, first, this plot on the bottom left is showing the traditional kind of cyclic stress ratio versus cone tip resistance plot that a lot of us use to assess whether liquefaction will trigger or not at a site. And these have been developed using case histories largely prior to 1999. So if you use these triggering procedures by Idriss and Boulanger or by Ander Chetin or some of the more recent ones, they're not incorporating a lot of new data in there because it takes a lot of effort to develop these case histories, use judgment to pick the representative QC1 NCS and all that stuff. So we've added now a bunch of new data, and we've gone through an exercise of taking our CPT layered data and identifying critical layers from that. So we've applied a whole bunch of different criteria to it, like which layer has the lowest factor of safety using a traditional triggering relationship, which one has the biggest gradient of LPI, which is a parameter that's integrated with depth. And so you can see on the right side for this particular profile, which is from Taiwan, Wufeng, 10 of the different criteria picked the same layer as the critical layer, that one. So we said, all right, that's the critical layer. Let's plot it on the curve. And the open circles here mean no liquefaction manifestation, and the filled in circles mean yes liquefaction manifestation. So usually if you plot above that curve, it means there will be manifestation of liquefaction. But wow, here's a site that has a sandy soil, right? I sub C is less than 2. It's about 1.7. So maybe fine sand or medium sand. Fairly low tip resistance. QC1 NCS is under 100, and the CSR is up there around 0.8. And it didn't manifest liquefaction at the surface, right? And so we were getting a lot of these sort of false positives where the model is predicting liquefaction, but it wasn't observed. And when we start looking at these cases, it's easy to see why. This is a pretty thin layer, and it's at a depth of about 6 meters below a pretty thick cap of clay. So we think probably that layer did trigger. I bet it liquefied. It just didn't come up to the surface. So nobody knew about it. And it's like, well, yeah, but then who cares, right? If it liquefied and it didn't cause ground damage or anything like that, maybe there would be a little settlement of a building or something, but there was no manifestation. So the thickness of the layer matters, the depth matters, whether there's a capping layer matters. Some of Professor Ishihara's work showed that back from the 80s. So what we've been doing now is looking at this problem more from a probabilistic framework using Bayes' theorem, noting that there's some probability of manifestation given triggering, right? We've treated that as kind of being one in the past. We haven't separated triggering from manifestation. And then there's some probability of triggering given no manifestation. You could have cyclic softening of a clay layer, or you can actually get sand boils before liquefaction happens and things like that too. So we can use Bayes' theorem in a couple of ways. We can say, okay, given that we did see manifestation at this site, what's the probability that it triggered? Or given that we saw no manifestation, what's the probability that it triggered? And then we've more recently been using these functions for the probability of manifestation of a layer conditioned on triggering of that layer that are logistic functions. So this is a logistic regression technique. And I'm showing 3 examples. This is depth, tip resistance, and soil behavior type index. And we would expect as the depth of the layer increases, it's less likely to manifest at the surface because the sand would have to travel up much further to get to the surface. As the cone tip resistance gets higher, the soil is more dilative. It's probably less likely to manifest. And then as I sub C increases, it's more clay-like. Clay-like soils don't tend to liquefy or manifest as much. So these are actually regressed from the data, and they're showing the right trends, right, which is always good. And so the method that we've taken is to do this logistic regression to back out the beta values in that equation. And then there's also a characteristic thickness of the layer that we're getting from the regression also. And then instead of predicting manifestation of a layer, we're predicting manifestation of the profile, given all of the layers. So we're considering contributions from every single layer in the profile to manifestation at the surface. And there's a cost function on the bottom. That's what we're minimizing. It's a little different than least squares regression because data are classified as yes, no. It's not a continuous variable. So that's why we're doing the logistic regression instead. And logistic regression, I think, is machine learning. I was asking Jamie, we don't really know. It does give you an equation in the end. So it's not like you just have to use this neural network model, but I don't think it's that much different from least squares regression. And we're getting a true positive rate of 76%, which is not great. We need to work on that a little bit more, right? This is very preliminary information, and true negative is 58%. So I think we'll be able to improve on this. And that was my last slide. So thank you.
Thank you very much, Professor Brandenberg. Okay. So I guess this is for Professor Adrian Rodriguez and Professor Mohsen Zakir. Oops. Oh my God. That's a big question. For S to S and R squared comparison, do ML-based models use the same input of baseline ground motion models conditions on VS30 and Z1.0?
So the answer is, well, we tested different things. The main idea was to use different inputs. In fact, the GMM model uses simply those two proxies, whereas our EHVSR, the whole horizontal to vertical spectral ratio, that is those ratios at all frequencies for the proxies. So the input for the two machine learning are the input for the ground motion model is different input to the machine learning. And what we showed is that when we do that, we improve on the performance. When we use the same input for both, that is only proxies using the machine learning tools we use versus traditional derivation based on our understanding of physics, we did not really improve on the predictions. But this is because we use, if we had used maybe much more nonlinear or deep learning tools, then it would have been a little bit different. In fact, we know it is.
Yeah, but it's yeah.
I hope I answered the question. I also answered the question in the chat as well.
Yes, okay. So there is another question here for Scott Brandenberg to share your contact email address. Okay.
I'm not connected, should I type it?
Oh, yeah. Maybe.
By the way, Scott, thank you for the work that you all are doing with these databases, because they are extremely useful for everybody.
Oh, sure. Sorry, getting a lot of feedback here. I'll step away from the mic. Thanks, Adrian. It's good to see you virtually from across the country anyway.
All right. Thank you, Professor Brandenberg. Okay. Is there any other question or comment?
I can make a comment. It's just on the presentation by Dr. Kumar. I think it's fascinating the work that they have done to obtain physics from the machine learning, and I think that's something that's our long-term objective as well. But it's very interesting to see the progress that they have done in the research group. But I think that should be something that everybody that's doing work on machine learning should keep in mind. It's not just a question of having a black box that gives us an answer, but trying to extract information from the black box that enlightens the physical model. So just kudos to them for having taken it this far.
My question's for Dr. Brandenberg. You were talking about processing ground motions. We wanted to get the raw ground motion data from your database. Is that in there, or is it only processed?
Yeah, thanks for the question. We only store the processed records, but the GM process program produces an HDF5 file that has the unprocessed data in it. So if you wanted to do your own processing or like extract a noise window, pre-event noise to look at that amplitude and stuff like that, it would all be in there. We have to figure out how to share those too, because those are like huge files. The small ones are 500 megabytes, stuff like that. So some of the events have hundreds or, a lot of records. And so the unprocessed data will probably be there. But yeah, our time series are all just the processed ones right now. Yeah.
This one is for Professor Brandenberg. What are the input and output for the model, for which we saw the confusion matrix for in his last slide.
Yeah, so that confusion matrix was from the logistic regression that we've done. So I kind of rushed through it, but there's an equation where we had those beta parameters. There's a logistic regression equation or a logit equation where the probability of manifestation given triggering of a layer depends on depth to the center of the layer, the tip resistance within that layer, and then the I sub C value or the soil behavior type index. So what we do is we assume a triggering model. We're using a lab-based triggering model where we say the probability of triggering liquefaction is based on this equation. It's a function of cyclic stress ratio and cone tip resistance. And then we assign a probability of manifestation to each layer based on its probability of susceptibility, its probability of triggering, and then the probability of manifestation given triggering. So we have like a continuous profile of the probability of manifestation. And then there's a product sum. Well, and that probability will depend on depth and stiffness and other things too, for whether it will manifest. And then the probability of manifestation of the profile is the product sum of the probability of manifestation of the individual layers. And it's actually the product sum of not manifestation is equal to the product sum of not manifestation of each layer. So there's a bunch of 1 minus in there, right? And so the confusion matrix that we have is a very preliminary regression where we've come up with the coefficients for those logit functions for the conditional probability of manifestation given triggering. I didn't show it, but so if you look at like the confusion matrix from the Boulanger and Idris 2014 model, it's really much better than what we showed. It's 80%-ish for both true positive and true negative rates. But if you include all the new data in there, it's not as good, right? They drop quite a bit. There's actually a lot of false positives. And so ours is an improvement on that, but I don't recall the numbers. But yeah, this is all like really brand new stuff. There's no publication yet. We just submitted our preliminary report like this week, and I got permission to show some of it here today from Steve Kramer and John Stewart and all the collaborators I've been working with. So it's brand new, and I was maybe deliberately vague on showing the details.
All right. Thank you, Professor Brandenberg. So let me check if there is something else here. Seems to be that several questions have been already addressed and answered already. So, is there any other question here, Professor Jamie? Please.
I'll pose one to the person sitting next to me, but I'll come up here to ask a question.
All right. So one of the first example that you showed, Krishna, that walked through the liquefaction prediction, I appreciated how systematic you were about showing building the decision tree and the random forest, and then going through the shaping, the trends, and does this make sense, and questioning it. Can you talk through a little bit more how you use that to restructure the model to kind of impose the limits that, if PGA is smaller than you'd expect the likelihood to increase? How do you actually impose that? You said kind of artificially this 0, but can you talk me through how you leverage that insight to really update the models?
Yeah. Like the first part of the work, which is to show that the model was actually learning the bad physics, which was high PGAs don't liquefy and low PGAs liquefy. When I went and told Professor Rachi, it was like, this is bad. That's how it kind of started. And you can't go, the one way is maybe remove those data out from black box model. And then whereas the better approach would be to build something much more transparent, like I was showing the graph. And you see that a graph is going in the wrong direction. You could use physics equations to then change the score. Because it's just a graphical equation, you can literally move the graph on and say, and that's a black box machine learning model. I wouldn't know how to fix a black box model other than removing the data out or giving a warning saying, don't try this over this PGA range. But that's why it's easier to work in a glass box model, because now if you find something incorrect, you can go change those equations, but you have to change all the other correlated parameters as well. That's the challenge.
This is for Krishna. So Krishna, with regards to the SHAP, the SHAP, how you essentially extract the physics from the model, the process in which you do that, is it that you go through multiple iterations and go into the black box and see what iterations, the heat map, is it generated by the SHAP model, or do you have to do something to essentially get that out to try and figure out the physics that it's using specifically?
I showed two different post-hoc explainers. One was Shapley, and the other is GradCam. And I think there are other speakers who will talk more about GradCam and ScoreCam. GradCam is the one that generates heat maps, and it will look at the last layer of your convolution network and do that propagation to calculate to see what the network is. In order to understand what the neural network actually sees, I think doing the inverse neural network was a much nicer way to look at it. You can plot feature maps, you can plot saliency features, but they don't consider what the input image is. So what we do is use something called total variation scheme, which is used in electrical engineering to do denoising. And we use that to do the inverse process. Our inversion at the moment is unconstrained, but like for us, the dispersion curve is normalized between 0 and 1. We hope our inversion ends up between 0 and 1. And we've tried some loosely constrained algorithms where it goes slightly below and slightly above. Doing a fully constrained inversion is still harder, but it gives you a general idea of what the neural network looks like. Whereas if you want to get the actual physics, like for the last example, which again, Professor Rodriguez mentioned about deriving physics equations, that was our hope. It was great to see that it actually learned the physics equations, but it also means now we can embed much more. There are a lot of physics we put into that system to make it better. So I glossed over a lot of factors because I only had 5 minutes to talk about graph networks. So we put in conservation of momentum, we put in conservation of mass, and we cheat when we put in conservation of mass because we don't put in mass into the system. And if you don't put in mass, the machine learning model doesn't predict mass, so the mass is automatically conserved because you've always set mass to the system. So instead of making the machine learning model learn the entire physics, if you know a lot of physics, like an explicit time integration scheme, if you know conservation of mass, conservation of momentum, you're kind of restricting the model to learn what new physics it needs to know. So you can say, oh, gravity acts downwards in the vertical direction all the time. It only needs to figure out what the other accelerations are. Instead of trying to learn explicit integration, gravity, particle collisions, you kind of put in all the known physics and say, go ahead, figure out what the unknown physics is.
Explicitly describe the known physics
to the graph networks so that you can make it do your known physics. Our hope is maybe one day we can look at experimental data with high-speed cameras, make the graph network predict the same dynamics, and then use symbolic regressions to derive those physics equations out. So that maybe we'll be at a point where we can derive constitutive models by looking at experimental data. And I always say, this is a joke, and hopefully maybe it will be a reality in 5-10 years. There's DALL-E, which does text to image. So if you haven't done it, here's the rest of your day spoiled. You can type in text and then it will generate images for you. There's also OpenAI, which writes text for you, and our code derives equations for you. You basically put 3 of those things together, you have an AI PhD student. And then they will be able to write papers in the future. But I think we want to be able to use AI to discover new physics and not replace what we already know.
There is a question here for Professor Rodriguez-Marek.
So for Adrian and Moshe, and I really enjoyed your presentation. My question is about the HVSR part. So I actually have two questions. First, HVSR data usually has really a large number of data points because it's recording a long time series in order to go to low frequencies. So when you say you're using the full spectrum, is that decimated in some way? Like where the tables were hard for me to read. Are you taking certain frequencies or smoothing it or doing anything like that before feeding it into the algorithm?
I can take this, and Adrian can comment if he wants to comment on that. But the HVSR data that we use was kind of an open source database by Zhu et al. They were, generous enough to provide more data on that. And you're right, there are a lot of points in that. We took from 0.1 hertz to 30 hertz, and there was some cutoff on that. And they did the whole smoothing with the, the smoothing on that HVSR spectrum. And we used those frequencies as the raw data in our machine learning model. But as you know, machine learning models usually do some kind of normalization when you feed raw data to them. And we just followed like a standard normal transformation because we didn't want because we had derivative proxies and HVSR spectrum, and we didn't want those overpower the input space to kind of shift our machine learning models to prediction based on the ones that has larger magnitude. So there was some normalization, but it was for the sake of making everything more balanced in the database, and we use certain frequencies in HVSR space.
My other question is about whether there is a peak or not in the HVSR, because a lot of sites will not exhibit a clear peak when you look at it and you think, why is there no peak in this HVSR data? And then other ones do have a peak, and some people have claimed that the ones with the peak are those are more one-dimensional sites that may have an impedance contrast and amplification at a certain frequency. So I'm just wondering about, do you need to feed in the entire spectrum for sites that really just don't have a peak and they're kind of flat everywhere? Are there features in that HVSR spectrum, even in the absence of a peak, that are still telling you something about site response?
That's a great question. Adrian, do you want to go first, or should I?
Let me just. Our approach was to use the entire spectrum to let the machine learning tool make the inference as to how important is, or what information is in sites that we do not have any peaks. So we did not filter out those sites that do not have any peaks. The result does show that there's a clear correlation between the amplitude of HVSR at a given frequency and the site response at that same frequency. So there is information that's brought across the whole HVSR spectrum that informs regarding the site response. That's not to say, however, when you do go down to only extracting derivative parameters on the HVSR, those alone do not work as well as the entire spectrum, but of all those parameters, the peak frequency is the one that works the best. So that peak frequency still contains a lot of information. However, using the entire spectrum does provide better results than using just derivative parameters. What we need to do is follow Krishna's example and try to extract what is it what information is it in that entire spectrum that's informing about site response. So that's something we got some inspiration today. Jorge Macedo asks on the difference between EHVSR and MHVSR. And that's a very good question, because the EHVSR obtained from earthquake records, so in a way it's cheating, because we are using the records themselves to inform our predictions. MHVSR, they are obtained from noise measurements, so they do not have the record. And the answer is mixed. When we try to use noise models to predict some of the things in the same database that we use on MOSEN, it didn't really work, not with the machine learning tools that were presented today. But when we use neural networks on a different database, then both we got really good results using noise measurements. And that's not surprising, because noise HVSR and EHVSR are indeed correlated. So that's the direction that we are going right now in our research, is using noise measurements of HVSR, and the initial results are promising.
Adrian, thank you. I'm not sure if you can hear me here.
Yes.
Just a quick follow-up. In the case of the HVSR model, this is based on microtremors, and you may not be as have a recording that is close by from the microtremor. How will you proceed on that case to look into the amplification?
When we're using noise recordings, it's simply windowed measurements of noise. So we are not trying to make any inferences about where that noise is coming. It's ambient noise in general. So it's not microtremors. I don't know if that's the appropriate term. That there's a whole discussion in the community that deals with these recordings, differentiating anthropogenic and tectonic microtremors. We are using noise, period, just taking windowed measurements at the station. In fact, excluding any time there is some type of non-stationary signal, and using that to get the noise.
All right. So I think that if we are almost on time. So if there is not any other question or comments, we would like to thank our speakers this morning. Session number 1, Professor Krishna Kumar, Professor Adrian Rodriguez-Marek, and Professor Mohsen Zucker, and Professor Scott Brandenberg. Thank you very much for your presentations. And we are going to have a 15-minute break, and we are going to resume with session number 2 at 10:30 in the morning Pacific time.